Hello dear students, in this lecture we will continue our discussion on plasma properties of geospace, in which we are looking at several interesting aspects about plasma, how it is different, etc. So the fundamental property of plasma or the behavior of plasma is to remain electrically neutral. So any local charge displacements or charge islands in the plasma created by any external force will be nullified by plasma oscillations, and we have derived a expression for plasma oscillations. Now, when plasma has an ability to show something called as collective behavior. What does it mean? It means when plasma is subjected to electric and magnetic fields, it will behave in such a way to shield this external electric and magnetic fields, or so as to say that the extent of this external electric and magnetic fields will be limited only to a particular distance. The entire plasma will not feel the presence of these electric and magnetic fields. So this characteristic distance is called as the device length, also known as lambda d. So device length, it is a length parameter over which the external electric field will have some influence on the plasma. So in this class we will not derive the entire mathematics of this device length. Rather, we will directly use the expression. If you are interested to know how this device length can be derived, you can refer to the NPTEL lectures on plasma physics and applications. Okay. So we call it as the potential, device potential, as e to the power of minus r by lambda d into q by 4 pi epsilon naught r. So this is called as the device potential. So this one is the Coulomb potential that we are familiar with. Any charge q, the potential due to any charge q can be written as this. You have an additional term e to the power of minus r by lambda d, in which lambda d is a scaling parameter. Every distance is scaled in the units of lambda d. So what will happen is, if you have a positive charge kept inside the plasma, a cloud of electrons will surround this positive charge, and because of this negative charge concentration around the positive ion, the effect of this positive charge cannot be felt, or this positive charge becomes invisible for any point in plasma beyond this cloud. So the radius of this cloud, or the spatial extent of this cloud, is given by lambda d. So what this expression shows is that up to a particular distance, the screening of the positive charge or the foreign charge can be felt. So this is the expression for lambda d, which is called as the device length. The device potential is given here. Now we will look at an expression for device length itself, which we are not going to derive anyway. So device length can be written as lambda d is equals to under root epsilon naught kb Te divided by n q square, where epsilon naught is the permittivity of free space, kb is the Boltzmann's constant, Te is the temperature of electrons, n is the number of charge carriers per unit volume, q again is the charge. So the units for this are meters. In terms of plasma frequency, the device length lambda d can be written as omega p inverse under root kb Te divided by me, mass of electron. These two expressions can be very handy to understand the state of plasma in the geospace. Again, like I said before, we have not derived this expression, we have directly used this expression for our discussion here. Right. Now, Depending on the dimension, or depending on the lambda d, we can also define the second most important plasma criteria. So plasma criteria is that condition which must be satisfied by by an ionized gas to be called as plasma. So device length lambda d defines if the length scale of the plasma system is capital L, or the extent of the plasma system, the scale of the plasma system is capital L, the device length must always be very, very small in comparison to the length scale of the plasma system. So this becomes the second plasma criteria. So the earlier criteria was between the plasma frequency and the collision, collision frequency, or the mean free time between the collisions of uh, plasma oscillations. Right. Now, with the help of device length, since it is a length parameter, we define what is called as ND, the device parameter, which is again, if you imagine a sphere with a radius r equal to lambda d, with a radius r which is equals to lambda d, and the number of particles, plasma particles within this sphere is called as the device sphere, and the number of particles within this sphere are called as ND. ND can be written as N naught, number of particles per unit volume, into the volume which is being formed by device length radii, 4 pi epsilon naught kb dE by Ne square 4 by 3 pi r cube. R is the radius, which is lambda d. Okay. Now, in terms of ND, we define the third plasma criteria, which says the number of particles within the device sphere must be very large than 1. Okay. The meaning of these three plasma conditions can be simply said as, the first condition says the oscillations must happen within one collisional time, the first condition says the oscillations must happen before the collisions happen. The second condition says the device length should be very, very small in comparison to the scale of the plasma system. The third condition says the number of particles within the device sphere must be large, very large. Okay. Now, with this fundamental understanding, we will now move ahead to discuss what is called as the gyrofrequency, or plasma being electromagnetically active entity moves from one point in the solar system towards the other point, for example, the solar wind. So, solar wind is a magnetized plasma in which the magnetic field is frozen into the plasma. So, as they move, they carry the magnetic field along with them. And when this magnetized plasma interacts or comes in contact or comes near the proximity of the Earth's magnetosphere, it will interact with the Earth's magnetosphere in different ways. Depending on the interaction, the entry of the plasma into the Earth's atmosphere will result in various phenomena. Now, it is very important to understand how plasma or plasma's movement changes, or how it can get affected by the presence of electric and magnetic fields. This is a very elaborate discussion in which there are many aspects, or depending on various ways in which you can define the electric and magnetic fields, the motion of plasma will differ in each of the case. Okay. We will not discuss all of that here, but what is important for us is to understand two crucial aspects. One, how the plasma moves, or how the plasma behavior changes when it is subjected to an electric field and when it is subjected to a magnetic field. Because when the plasma particles are subjected to the magnetic field, we will see what is called as the gyro motion, or which gives us what is called as gyrofrequency. Okay, so we should know what is gyrofrequency, because the way gyrofrequency changes and in the ionosphere or in the magnetosphere is representative of many ongoing physical processes in these regions. Okay. Now, as a simple example, we will take a static electric field, and we will see how the plasma will change. Plasma will move in a static electric field. So, a static electric field, we will take it as electric field E, a function of whose components are 0, 0 and Ez. What does it mean? It means electric field has a single component along the z direction. Now, the particle can have a velocity v, which is vx, vy, vz. To understand the motion of plasma now being considered as a particle subjected to the electric field, we have to see that this particle is experiencing this electric field. There's a basic point. So, we will write the velocity. It is in the electric field. V as Vx I cap plus Vy j cap plus Vz k cap. So, the force that the plasma particle experiences because of the electric field is Q times E. So, m d square r by dt square is Q times E, or m d by dt of Vx I cap plus Vy j cap plus Vz k cap is equals to Q times Ez. Matching the components on the x on the left hand side and right hand side, you can write m dvx by dt is equals to 0, m dvy by dt is equals to 0, and m dvz by dt is Q times Ez. So, the velocity along the x direction will remain unaffected due to the presence of an electric field along the z direction. Similarly, velocity along the y direction will remain unaffected due to the presence of electric field, and velocity along the z direction is changing. So, along z direction, it is an accelerated motion because of the presence of a non-zero electric field. As a result of this, what can you say? So, if you consider only this equation, what you will realize is Q being positive or negative, you put Q to be positive or negative, you will realize because of the presence of electric field, oppositely charged particles will move in opposite direction because the force itself is dependent on the charge polarity. So, as a consequence, when plasma is subjected to an electric field, it will lead towards charge. So, negative charge here and positive charge here. It will lead towards charge separation. As simple as that. This is what I wanted to emphasize without going into the complete discussion of plasma's movement in the electric field. Of course, this topic, even the topics that I'm going to discuss, are elaborately discussed in plasma physics and applications. You may always refer to those discussions. Right. Now, the second thing, one consequence which emerges naturally out of this equations is that you will realize that d by dt of half mv square plus q phi is equals to 0. So, half mv square is the kinetic energy and q phi is the electric potential energy. So, particles movement in the electric field will be in such a way that the total energy will remain conserved. Okay. Now, you try to understand what does it mean. Okay. Now, let us take the example of the magnetic field. So, this is not going to be entirely different from our basic understanding of the Lorentz force, which says any particle with a non-zero velocity will only be influenced by the magnetic field. If a particle has a charge q and if it is not moving, the magnetic field will not be able to influence it. So, which means if you want to understand the behavior or the rate of change of velocity of the particle under the influence of magnetic field, you can start from the fundamental Lorentz force equation, which is q times E plus u cross b, right. Now, in this situation, we are going to take the electric field to be 0 because we want to understand m d square x by dt square is q times v cross b or u cross b, or rather we can write a generalized d square r by dt square. We can simply modify this expression m v dot m dv by dt is v dot q times v cross b or u cross b. I'm just referring to the velocity, right. So, this can be written as d by dt of half mv square, divergence of curl. We know that the divergence of curl is 0. So, when the particle is moving in a uniform static magnetic field, why am I calling uniform and static magnetic field? Because the behavior of plasma or the movement of plasma will be entirely different when if you don't include these two assumptions, which are uniform and static. Uniform means the strength of the magnetic field not changing as a function of space. Static means the strength of the magnetic field remaining constant throughout the time. Okay. So, when the particle is moving or when plasma is moving in a uniform static magnetic field, the rate of change of kinetic energy is 0. That means magnetic field is not able to do any work on the plasma. Right. This is what remains conserved when plasma is experiencing magnetic field, plasma in magnetic field. But this does not tell you how the particles will gyrate or what is the frequency that is associated with the gyration. Okay. So, for that we have to do a little bit more than this. So, what I will do is I will tell you how to begin the mathematics, and then if you do simple algebra, what will you get or what you can get. Okay. So, we have to see the same equation m d square v by dt square is q times v cross b. So, you can take v as vx I cap plus vy j cap plus vz k cap and b as bx I cap plus by j cap plus bz k cap. The vectors written in the form of in their components. So, for simplicity, we will make the velocity to be 3-dimensional in nature, and we will make the magnetic field to be simple as 0 plus 0 plus bz along k cap. Okay. Now, how do we move from here? We have to resolve this curl. So, resolving this curl will have, so v cross b is I j k, this is vx, vy, vz, 0, 0, bz. Okay. Now, you know how to solve this, which means you are going to get 3 components, something in the multiplication in the multiple of I cap, and something in the multiplication of j cap, and something in the multiple of k cap. Okay. Okay. You can get 1, 2, and 3. You will have to equate this to m dv by dt. Okay. So m, you can equate them, and the resulting equations that you get will look something like this. M d square Vx by dt square is equals to q Vz d Vy by dt m d square Vy by dt square is minus q Bz d Vx by dt, and m d square Vz by dt square is equals to 0. These three equations tell you how the particle is moving with time, or how it is changing with respect to time. If you uncouple these three equations, you will get simple equations in terms of Vx and Vy and Vz. D square Vx by dt square plus omega c square Vx is equals to 0. Similarly, Vy and Vz will be a linear motion because the magnetic field will not act along the parallel component, right? So this equation, or if I write an equation which appears before this, so d square Vx by dt square plus qb by m whole square Vx is equals to 0. So this equation is again similar to the plasma oscillations that we have derived. So this term must be omega square. So now taking this out, omega c is square root of qb by m. So when the particle is experiencing homogeneous magnetic field, the particle will move in a circular path, and because of the non-zero velocity component along the z direction, which happens to be parallel to the magnetic field, the particle's motion will look something called as a helical path. So the fundamental frequency, or the number of revolutions per second, is given by this omega c, which we call as the gyro frequency. Okay, and the radius that is associated with is RL. This is called as the radius of gyration. And most importantly, the particle's gyration frequency is dependent on the mass. So heavier particles will have smaller frequencies, and lighter particles will have larger frequency for the given strength of magnetic field. Okay. So which means that the amount of the number of oscillations, number of revolutions that the particle will complete will depend on the mass. This is an angular frequency, of course, and we define the gyration opposite. So the positive charge particles will move something like this, whereas the negative charge particles will move in the opposite direction. Okay, and their movement can be understood by simple notation. So we write q omega c as qb by m, which is omega c as minus qb by m, which is positive for electrons, and qb by m minus qb by m, which is going to stay negative for ions, because I am putting q is equals to plus or minus e into these expressions, then I get that meaning ought. Okay. Now, as an exercise, you can solve this mathematics, in which you can start from the equation F is equals to ma. You use force as q into v cross b. You get expressions for omega c. You solve it further. You get equations for Vx or r, the position, how the position changes with respect to time. Or we can say, instead of r, it's better to write x, y, z. Okay. Then you will realize that x and y, x square plus y square, or more generally, Vx square plus the equation that you're going to get, Vx square plus Vy square will look similar to an equation representing circular motion with a characteristic radius which is called as the gyroradius, which is equals to V perpendicular square divided by omega c square. So, if you V perpendicular is the perpendicular component of velocity, the gyroradius can be written as m V perpendicular by q b. M V perpendicular by qb, and omega c is qb by m. You look at these two parameters. This is the radius of gyration and this is the gyrofrequency. Let us write it down. Radius of gyration, and this is gyro or gyrofrequency, some people call. Okay. Now, the radius with which the particle will circle in the presence of magnetic field seems to be directly dependent on the mass. So, more the mass, the radius will be larger. The remaining things are going to be the same, right? So, ions will gyrate in larger circles and electrons will gyrate in smaller circles. What else changes? The frequency of this, the number of rotations that these particles will cover per unit time seems to be dependent in inverse way. Okay, higher the mass, higher the mass, the radius will be larger and the number of oscillations will be smaller. It is, of course, it is matching very well with the common understanding, right? But this is what we should remember. So, in those places where the magnetic field strength is larger, you can expect, now the magnetic field strength also seems to be deciding RL and omega c, right? So, magnetic field strength being very large will result in radius of gyration being very, very small, and at the same time, the frequency to be very, very large. So, okay. Now, the balance is what you have the magnetic field, you have the mass, and you have omega c, and then you have RL. So, omega c is qb by m, RL mv perpendicular by q. Right. Let us write. So, if the magnetic field strength is large, we will keep mass constant. Omega c will be large. The radius of gyration would be small. Opposite. Right. Now, let us keep the mass. Let us keep the magnetic field constant. If the mass is large, that is for ions. If the mass is large, omega c will be small and radius of gyration would be large, and if the mass is small for electron, the frequency will be higher and radius would be smaller. And because of the charge being positive or negative, the sense of rotation for electron and ion will be exactly opposite to each other. Right? This is the simple discussion in which we try to understand basic concepts. We didn't attempt to derive these elaborately. We are just trying to understand the basic concepts. If the particle is moving in a magnetic field, how do we see the particle's trajectory as a function of time? So, we realize that the Vx or the perpendicular components, if you consider the magnetic field to be along this direction Vz, the parallel component of velocity, which is Vz, will remain a constant, whereas the perpendicular components of velocity will be responsible for the gyration of particle around the magnetic field, around the imaginary line I have drawn. Okay. Why is the particle moving like this? Because of the non-zero parallel velocity. Okay. So, these are some fundamental concepts about plasma's movement in electric and magnetic fields. So, what we have learned in the discussion of plasma properties of geospace is that we have considered the geospace, we have defined what is geospace, and we realized the majority of the state of matter in the geospace is plasma. So we touched upon very fundamental aspects of plasma physics. Like I said, if you're interested to understand, or if you're interested to in working out the mathematics of these topics, you can always refer to the NPTEL course on plasma physics and applications.